All right, today we have a very special guest who I get to talk to about some really interesting stuff. We have Leo Pekelis from Gradient. Hey, Leo.
Hey Matt, how you doing?
I'm doing very well. So, Leo is the chief scientist at Gradient, and Gradient is a platform where you can put together different building blocks to build agents at scale. Prior to Gradient, Leo owned AI research at companies like CloudTruck, OpenDoor, Optimizely, and Pixar. He also holds a PhD in statistics from Stanford and also completed his undergraduate economics and math degrees. So, very qualified to be talking about what we're going to be talking about today, which is context windows. And why I'm especially excited to talk to Leo today is because Leo and the team at Gradient have been able to unlock a million token context window for the LLaMA 3 model. You know, LLaMA 3 is my favorite open source model right now, and being able to have a million token context window versus what it comes with out of the box, which I believe is 8K, is tremendous. And they've been able to do this. And we're going to talk about how they were able to do this and why it's important. So, Leo, why don't you start with just explaining from the broadest view, what is a context window as it relates to large language models?
Yeah, that's a really good thing to pin down. You know, maybe to even taking like a few steps back before that. If you kind of think about what language models used to look like a number of years ago, it was a lot of kind of pre-training the model first, and then kind of setting it going, and then seeing kind of output it produces. But I think what folks, and this was pioneered by a lot of folks who are researching at OpenAI, is they found that these models, the way they work is they're autoregressive models, meaning that they create one token after another to produce their output. And if you kind of seed that output with some amount of input tokens, you can actually direct where the model goes. And that kind of like sets up the whole idea of a context window, because if you train a language model in the right way, you can write instructions to the model, and then it'll kind of continue where you left off in creating the response. So that context is exactly that. It's the either the instructions or the chat history, or really what you seed that sequence with, that the language model is then going to run with after that.
All right. So if somebody is typing into, let's say, ChatGPT, the number of words tokens that you can put into that input as the instructions to ChatGPT plus the output, those two things combined are the token or the context window. Is that right?
Yeah, exactly. That's the total context length.
Okay. And when ChatGPT first came out, I believe it was 4,000 tokens context window. Then we saw other companies come along and increase that. ChatGPT now, I believe, has 128,000. Claude has more than that. I know Google's Gemini has 1 million. But why is context window so important? Why is having a larger context window important? Why would somebody want that?
Yeah, sure. So this kind of like boils down to now how people interpret kind of like different parts of the language model and try to map it across how humans operate. And so you can think about context window is what a model is holding in its kind of like working memory. Maybe if you're preparing for a test or something, maybe you like quickly study up on chapters and you have that like fresh in your mind. Versus maybe what the model is trained on or fine-tuned on, maybe somewhere like deeper in the memory banks. And so expanding that context window just allows a model to hold more in its working memory. And in particular, what's really cool about working memory, language models that are all based on transformer architectures, right? Like the idea that attention is all you need. When more and more tokens are being able to put into the context, the model is able to intend over all of them. So now the language model is able to perform whatever complex reasoning it can do, sort of like the great ability of language models like ChatGPT that we see over more and more data. So there's kind of like less pre-processing and summarization and kind of like stuff that you need to build up outside of the language model. So you can kind of let it do more of what it's good at.
So I guess in the earlier days, and by the earlier days, I mean like a year and a half ago,
Right.
you could maybe fit a few pages of text into an input box for a large language model. Now you might be able to fit an entire book or multiple books. And then when you take into account multimodality, you might be able to fit a 30-minute video into it. And so that's really the power of the increased context size, is you could just fit more and more into it rather than having to kind of chunk it up and fit it in one by one. And it just makes things a lot more efficient and a lot easier for the large language model to understand what you're doing. Is that right?
Yeah, well, it's easier, more efficient, but it's also more powerful too, because exactly as you mentioned, chunking it up, it's kind of on you or on the user to figure out how to chunk up that information and how to summarize it. Whereas if you put all of that in the context window, now the language model is able to figure out, what I actually need is the 30th frame and the 67th frame and the 102nd frame from the video. And that's what lets me answer the question, versus like you needing to preempt or pre-cache that. So I think it's all of the above. It's faster, more efficient, and it's also more powerful.
Okay, so when we're thinking about large context windows, we understand why it's important. What are some of the use cases that can be unlocked with these larger context windows that would be prohibitive for shorter 8K, 32K context windows?
Yeah, exactly. So it's kind of interesting because at least for us, a lot of what we've done in the past and continue to do is work kind of with larger enterprise customers and solve some of their most pressing AI use cases. And really, you can just like go down the list of everything that we've done and pinpoint, I guess, short context pain points that we've hit, and how long context models are helping with that. And so to give an example, one of the projects we've been looking at is sort of extending kind of like the work of a coding copilot, right? And so like the way a coding copilot typically works is you're able to give it some kind of instructions, and maybe it'll give you as output the next function or something like that, right? Like maybe like tens or 20 lines of code. And kind of like the next step beyond that is asking an AI system to instead code up maybe entire feature, maybe entire like workflow or pipeline. But in order to do that, the system needs to be able to reference a whole lot more information, right? It may be like an entire code base or like multiple GitHub repos or something like that. And the way that, one way to approach that is through some kind of an agent system, right? Being able to fetch this information sequentially. The issue with that is it can end up being kind of brittle. And it's definitely going to end up being pretty slow and pretty costly because the model keeps needing to fetch more and more pieces of information. But as soon as you can now put all of that code base straight into the context in kind of like one shot, ends up being many fewer calls to the agent, but also the language model is able to reason in a more complicated and more complex way. So that's one example. There's more.
Coding is a great example. My favorite use case still to this day for large language models is to help me with coding. And typically I'm like pasting in like one bit of code, or even if you have something that is an actual AI coding assistant living within your IDE, it's typically has a context of maybe the file you're looking at. Maybe it has some sophisticated mapping where you can kind of get a sense of what the rest of the files in your project are doing, but typically it doesn't have a holistic view of the entire project. But with a million token context window, and even when we get beyond that, that's when you can start stuffing an entire project into a single input. And thus the model will have just a deeper understanding of how all of these files and the functions relate to each other.
Yeah, definitely. And it can even do things that surprises us every time that we try it. It'll take multiple disparate file systems or code bases and figure out how to integrate them together, which is kind of cool. We've been able to say, hey, how can we maybe implement this new particular topic in our code base? And by virtue of having both code bases in the context, it can now start to synthesize those together.
By the way, Leo, when you're coding, I'm just curious, what does your stack look like? What is your IDE? What are you using for your coding assistant? And then the model and how, like, what does that look like for you?
Typically use some flavor of VS Code. There's a couple out there. There's vanilla VS Code. There's also Cursor that I've tried out to use a couple of times. They're both pretty good. I think that's typically kind of like my go-to interface. And then, I mean, honestly, like what we've been doing more recently is using some of our own long context models and trying that out and seeing how that works. It's not by any means as well integrated, so that's like a little bit more of like back and forth, but that's kind of been worth it.
And how do you integrate, or like what does your workflow look like when you're actually using your like Llama 3 million context window?
I think one of the things, and maybe that's like one of the interesting areas of research for us and where we're going next, is how best to serve these models because at the end of the day, there's kind of like a lot of compute going on behind the scenes, and probably you would want these models to be able to answer in a fairly quick way. You don't want to like give it one query and then have to go and get a cup of coffee every time you ask it a question. But right now the versions that we have internally, since we built them, I think we can stomach a little bit of wait time. So typically what we do is we have them running internally on some of our internal clusters, and we will send them queries. What we've been trying to experiment with more recently is kind of caching the first part of that query. So like caching maybe like the code base, if we're continuing on this example, and then being able to ask like multiple questions based off of that. And then, taking that output and then running with it in a more standard workflow. So then you can use all your favorite, GitHub Copilot or what have you, to kind of refine it from there.
And when you say caching, what does that actually mean in the context of large language models?
Oh, yeah, certainly. So, maybe to make it very clear, the whole like computational bottleneck that occurs with these long context models is specifically in this attention calculation, right? Because for one of these models to be able to perform attention, it needs to be able to have every token be able to reflect on every other token, right? And so that's like token squared computations or something like that, if in the like straightforward naive sense. And so caching means that, okay, well, there's like a bunch of those tokens that maybe across many queries, they don't change, right? Like my code base is probably going to stay mostly the same across a bunch of questions. So the attention for those tokens with each other, you can quote unquote store that in memory and reuse that. It's not like quite that simple, but that's like the rough idea.
Okay. So I want to talk about how you were able to actually accomplish this, because it's not really an easy feat, and there are a lot of trade-offs between typically quality and context length. And then I want to know, I have a bunch of questions for you, but let's just start with like the highest level view. What does the process look like to take a model like straight from Meta AI, Llama 3, the base model, and extend that context window?
There's a couple of pieces there. We've kind of touched upon at least one of them already, but like the two main blockers or challenges is one on the computational side, right? These things, if you try to run a long context model on one GPU, it's going to choke pretty quickly. But then on the other side is if a model, like for example the Llama 3 model, the reason that Meta said that it works up to 8K context length, it's not that you couldn't give it a longer context length. You certainly can. It's just that it hasn't been trained on longer context length, and so it just wouldn't really know what to do with longer context length. And so that's the whole part of it. Second part of it is actually teaching a model, the skills of how to read over longer contexts.
I wanted to ask, when you take Llama 3 and you have and you're training it for a longer context, like what does that process actually look like? Is it more akin to the original training or fine tuning?
Yeah. So it is more akin to the original training, with kind of like a pretty big caveat in that the way that a model is able to tell the difference between whether a token is 10 tokens apart, or 2 tokens or 10 tokens apart, or 100 or a million tokens, is through how the positions are encoded. And this whole like positional encoding is really like kind of at the crux of how you extend the context length and give the model more ability to understand what's 10, 100, or a million tokens apart.
All right. So and Leo, I know getting to a million tokens hasn't really been done many times. Gemini has done it, but especially with open source models, I haven't seen many, if at all, other million token context windows, certainly not with LLaMA 3. Like, what are some of the trade-offs that you have to think about? Like, I know quality versus length, but like, how do you think about that? And then how do you make the determination where to make that cutoff on the context length? And how do you test all of that? I know a lot of questions there, but maybe you can just dive into all of that.
Yeah. Happy to dive into it. Yeah, there's a number of points there, so I'll try to touch on all of them. I do think one thing that I can point out is that, you're absolutely right. There are not a lot of long context models, at least hitting the million context length out there. And I think one of the reasons is that it's quite costly to do it. It's like the amount of compute that you need to train these things is a lot. But one of the things that sort of our team has been working really hard on, even before LLaMA 3 came out, it was we've been working on long context for a while now, is how to get that training to be more efficient. And I think both through, definitely a testament to the open source community. I think you can point to every part of our stack and sort of that there were influences from either open research or open resource, but we've built on that a lot, to the point at which I think, compared to what has been published on long context models currently, there's a large world model paper out there from Berkeley. Our training is something like 30x more efficient on the compute time. And as far as like their like sample efficiency, if you back it out, maybe even closer to like 100x more efficient in sample efficiency. And so, once that starts happening, I think training long context models starts being more possible. So that's kind of like the first part, I think, why we haven't been seeing too many long context models out there. It's just like it's been like wildly inefficient.
And Leo, yeah. Real quick, let me ask you a question. So when a model gets to me, you're talking about the compute intensity of training, but for an end user like myself, when I pull down a LLaMA 3 million token context window model, is that more compute intensive by the time it lands on my computer than the base LLaMA 3 AK?
Yeah, and that's kind of like the second part of it. So the first part is even training the model. The second part is using the model. And so no, it's no more intensive for that like first 8K context. But as soon as you start giving it like a million context, then it starts being a lot more compute intensive.
Okay, it's cool because you can kind of just default to using the LLaMA 3 million token context window. Just use the 8K, maybe go up to 32K, really save the compute on your local machine, but always have the option to have more. Is that a good way to think about it?
Yeah, exactly. And I think one of the things that we've been pretty careful about and keeping track of is to not degrade the original performance of the LLaMA 3 models. I mean, they're really great and really powerful models. And so it wouldn't be like necessarily a win for us if we like completely tank the performance in order to extend the context. And so that is something else that we incorporate into how we train these models, is to retain sort of the short context performance and really just like extrapolate that behavior to longer context. So exactly, you can sort of like use one model for both short and long.
All right. And when you're actually testing the performance of these models, right, because you said you don't want to tank the quality, I know there's a benchmark called needle in a haystack. Maybe you can talk a little bit about that. It's actually a buddy of mine, Greg Cameron, I believe, who kind of initiated that idea. Maybe describe what needle in a haystack is, how you run it against a million token context window, and then how many times you have to iterate on it to finally get the desired output.
Yeah. So I think needle in a haystack benchmarks are great because they're like incredibly evocative, and I think they really help paint the picture of what long context models are trying to do. But the rough idea is you have a haystack of information, and that could be, maybe a short story repeated over and over. It can be a bunch of essays. One thing that we've been doing to make it even like a little bit more of a challenging evaluation is throw all of War and Peace into the haystack, which I think is like 750,000 tokens. And somewhere in there, you put in one needle of information. And so then you ask the model to search through all of that context and find that one needle. And yeah, probably like if that was your only goal in life, there's probably an easier way to do it than to have a large language model find this particular needle. But I think there's been quite a bit of research in showing that this kind of like associative recall technique is kind of like the precursor for a model to be able to do in context learning, which is kind of like exactly what we were talking about, of being able to give a model a bunch of examples and then having it learn from the examples that you give in context.
Okay, so you drop a little piece of information in this ocean of information and you ask the model, hey, do you see something there? Do you ask a question about that piece of information? I just thought of something though. So that's really good if you have this like one isolated point of information that you need to pull. But what if, like, and is this a valid way to benchmark longer context large language models? What if you need to cross-reference information from different parts of a very large context? Is that a different, I don't know that maybe the right word, but is that like a different performance for the large language model? Is that the same as just pulling one piece of information? Because I can imagine if you throw a huge code base into a large context window and you want to ask questions, it has to know not only about this function here, but also how it relates to the other functions and then within the context of the entire project.
Yeah, certainly. And you know, I think it's a good point that there's a pretty far path from pulling one piece of information to be able to reason about an entire code base. And I think even Greg himself, and when he was talking about the needle in a haystack benchmarks, mentioned that it was sort of the first step in a sequence of benchmarks need to improve and iterate. And so definitely, you know, you can look out there across like different long context models. And by now they all just absolutely crush this needle in a haystack benchmark, right? If you're not getting like close to 100%, like
yeah, I think I saw yours. Like when the needle in the haystack benchmark gets output, you see this XY graph and it's green, 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 and maybe there's a little red, but with your version, it's all green, which means it was able to pluck that little piece of information from this ocean of information from anywhere within that context.
Yep, exactly. So our model is all green. Gemini's model is all green. And so how do you differentiate from there, right? Like clearly, like these models need to be benchmarked on something like slightly more complicated. And so actually there's, you know, we've looked at a few different benchmarks that people have put out for testing long context. And there's one really cool one from folks at NVIDIA called Ruler. And for them, instead of looking at just one task, they also look at needle in a haystack, but they actually extend it to like 13 separate tasks. And it's all different kinds of flavors. So you go from one needle, maybe to multiple needles. Maybe the needles have like different pieces of information, but they all have the same key. Maybe the haystack itself is now an ocean of needles. And so now like this poor model needs to pick one needle from an ocean of other needles. And another really cool one that they do is called variable tracking. And so now instead of kind of exactly as you point out, instead of just having one piece of information, they're interrelated pieces of information. So maybe you have like x1 equals 5, x2 equals x1, x3 equals x2. And so now it's asking to fetch across all of those and synthesize that information.
It's almost like telling the large language model to go on a scavenger hunt where the first clue leads to the second clue, leads to the third clue. And if it's able to do that, where each clue is dropped in sequence throughout the context window, I think that would be super impressive. So which benchmark did you say is maybe most like that?
Yeah, so it's called Ruler.
Ruler.
Like a measuring
And that's by NVIDIA,
ruler.
right?
Yeah, it's by NVIDIA. And we actually tested our models on Ruler. And currently we're sitting at fourth place on their leaderboard. And so that's just behind Gemini, GPT-4, and Cohere's Command R+. So we're kind of like in that grouping.
That's great, but GPT-4 isn't a million tokens though, right? So it's not quite apples to apples. I mean, Gemini would be, so that's fine, but is that a fair comparison if you're on the same leaderboard as smaller context window models?
So yeah, that's a good caveat. These benchmarks, because they're more complicated, they're only up to 128K context length. And so like we just like no one has looked at like this type of performance kind of like at this granularity for over 128K context length. And that's like one of the areas that we're looking into right now.
Okay, cool. Speaking of areas we're looking into, what should people be excited about, whether it's coming from Gradient or just kind of the large language model landscape itself, larger context windows, multimodality? What are you most excited about?
Yeah, all the above. I mean, I think there's a lot of different directions you can go from here. I do think one of the current issues is that there's few ways that you can actually use these models, right? Like you basically have to rely on someone like Google or Gradient to be able to host these models so you can use them. And at the end of the day, they take quite a bit of compute. So looking at various memory efficient ways to serve long context models, I think is very interesting to me. Because again, taking an analogy from the human brain, I at least I know for myself, I don't typically hold entire textbooks worth of information kind of like in my working memory. They're somewhere back there in the back of my mind, and I think about like, oh, maybe like this chapter would be useful. Maybe I think about that chapter. And so there are like extensions of these algorithms to do kind of like compression on certain parts of the memory and kind of like selectively open up that compression. And I think that direction seems to me like the most reasonable way to go to be able to make these models useful and in a pretty impactful and efficient way.
Awesome. And Leo, if people want to find out more about long context, more about you, more about Gradient, where should they go?
Yeah, definitely. So we have a Twitter account, pretty big presence on Twitter and LinkedIn. Folks can come find us or talk to us from there. We also have a Discord channel. Always happy to chat with folks and with the open source community. I think that's one thing that we've found a lot of benefit from is partnering with folks out there in the community and working on research projects together. So if anyone has any ideas or fun things to work on, we're always curious about that.
Great. And they can go to gradient.ai to find out more about Gradient's products. And I will drop all of the links, including Leo's Twitter and Gradient's Twitter, all of that in the description below. Leo, thank you so much for joining me today. I cannot wait to continue testing the LLaMA 3 million token context window, and can't wait till you get to 2 million. No pressure.
Yeah, we'll try to get there as soon as we can. Thanks, Matt. It was really fun chatting.
All right. Thanks, Leo. Bye.